The question that I have is, how do you analyze a rigid body subjected to static loading? In this chapter, we are interested in analyzing rigid bodies. So how does this differ from what we have done so far? To answer this question, we need to understand the difference between a body and a particle. Remember the cable systems like this we have learned to analyze, right? If you recall, this little ring that connects the cables was approximated as a particle, right? Mathematically, we have basically ignored its dimensions and then approximated this as a point. So a particle is mathematically represented by a point. Then to solve for the tensions in the cables, we used these equilibrium equations, right? In 2D, some of the forces in the horizontal direction is 0 and some of the forces in the vertical direction is 0. So we are able to write down two equations, two equilibrium equations for each particle, right? So mathematically we can solve for two unknowns, right? So we start from a particle that has at most two unknowns, solve those two unknowns, and then we go to the next particle where the unknowns are still less than or equal to 2 and so on, right? So we'll see in a second that just the force equations are not sufficient for a body. Furthermore, we note that if I come and section the cable at a certain point like we have done in this picture here, all we see is a tension, right? In other words, the internal force on the cable is just a tension, which is a force, not a moment, right? So this is going to change as we go from a particle to a body. The next important thing we note here is that the force on a support like a support A or B is just the tension in the cable that is attached to that particular support, right? So once we solve for the forces in the cables, the tensions in the cable, the forces in the supports are also trivially obtained, right? This is also going to change as we go from this type of cable system to a rigid body. Let's consider a simple two-dimensional rigid body like this one over here and try to understand some of the factors we talked about in the earlier slide. So this is what we call a cantilever beam. Just to define the problem a little bit more clearly, the beam is supported by what we call a fixed support at point A. We're going to come back and talk about several different types of supports in a little bit. The beam is subjected to a distributed load omega, a point load P, and a concentrated moment M node at point B. So to design the beam and the support properly, we need to know two things. We need to know the reactions at the support A, and we need to know the internal forces at any point along the length of the beam from A to B. So in this chapter, we're going to learn to calculate the support reactions, and then we will come back and learn how to calculate the internal forces in the future. So now let's see how this system differs from the cable system we talked about in the previous slide. So what is the first thing we do in the analysis? We develop a suitable free body diagram, right? So here's the free body diagram of the beam. So what exactly did I do? Well, I isolated the beam by cutting it out of the support at point A. So anytime we section a body like this, we need to realize that there are internal forces at the plane of sectioning. These internal forces are to be marked at either side of the plane. So here I am sectioning on this vertical plane. So there is a vertical plane on the beam and there is a vertical plane on the support, right? On this plane, there are internal forces. It turns out that in general, on a fixed support like this, there could be an axial force, a shear force, and a bending moment like this. So the axial force is the one that acts along the axis of the beam, and here I denoted that by AX. And the shear force is the one that acts parallel to the plane of sectioning, and here I denoted that by AY. And then a concentrated moment, MA, also acts at that point. Now you can compare this with the cable system where the force on the support is basically the tension in the cable, right? But here we have three of them. Of course, the forces in the wall here would be equal in magnitude to these forces, but opposite in direction to these forces. Now let's talk about the internal forces. If I were to section the beam at a point like point C and separate the beam into two parts, these are the internal forces that I will see in general. There will be an axial force, a shear force, and a bending moment. So once again, just to compare this with the cable system, in the cable system we just had one force, which is the tension on the cable, whereas here the internal forces consist of these three forces: shear force, axial force, and a bending moment. So as we pointed out earlier, we're going to have one additional equilibrium equation in the case of the equilibrium of rigid bodies. So that is the moment equation. In other words, you sum up the moments about any point for a free body diagram and set it to 0. Let me also make a comment here that the equilibrium equations can be any combination of the above. In other words, we can sometimes use one force equation and two moment equation, or two force equations and one moment equation like we have listed over here. The fundamental principle says that the total number of equilibrium equations cannot be more than 3 in the case of 2D problems like this. So that's the only restriction that you have. Otherwise, you have the flexibility to use any combination of these three equations. So here's a brief summary of the details of the analysis of rigid bodies. First, we recognize that to design a rigid body like a beam like this, we need to know two things. We need to know the support reactions, and we need to know the internal forces at any point within the rigid body. To calculate the support reaction, the first thing we want to do is to isolate the body to be analyzed from their supports. The next thing we want to do is to complete the free body diagram of the body to be analyzed. When you develop the free body diagram, you want to make sure that you mark and label the support reactions on it. Because of the importance of a free body diagram in an analysis, I want to come back and elaborate on this a little bit more in the next slide. So once you have the free body diagram developed for the body to be analyzed, then you use the equilibrium equations to solve for the support reactions. You can use a suitable combination of these three equilibrium equations. As for solving for the internal forces, we'll treat that in another chapter.